For the invitation. So in spite of the obligation to use the microphone, I want to encourage everybody to ask questions if there's anything unclear, except in the first 5 minutes of the talk. And the reason is the first 5 minutes will contain some motivation from string theory, and it will be painfully clear that everything I know about physics of string theory has been scraped together from survey papers. So you can ask me about the math, but ask that crazy physicist who came up with this stuff in the first place why this is supposed to model our universe, because I don't have any comments on that. But so the main chunk of my talks will be devoted to the construction of this so-called non-archimedean SYZ fibration. And so as I said, the motivation for the existence of such a structure comes from mathematical physics. So in certain versions of string theory, the universe is modeled by means of a 10-dimensional manifold. A real manifold. And where do these dimensions come from? So they're the 4 dimensions of usual space-time. And then string theory introduces an additional 6 dimensions, or some of the standard versions of string theory at least, which are supposed to be additional dimensions in which strings can vibrate and which explain the physical properties of particles that we observe. And so by imposing some conditions that well, the universe is supposed to satisfy, physicists have worked out that the most reasonable candidate for this 6-dimensional piece is a complex Calabi-Yau manifold of dimension 3. So this comes from a complex Calabi-Yau threefold. All right, why not? But then the story becomes interesting for algebraic geometers at the point which was somewhere in the 80s, when physicists realized that, in fact, the Calabi-Yau threefold is not uniquely determined by the physical properties of the model. So the universe does not uniquely determine the Calabi-Yau threefold. So they rather come in pairs. Which are called mirror pairs. And so mirror pair is usually denoted by a notation of the form x and x check. And so these are 2 different Calabi-Yau threefolds, so its geometry can be quite different at first sight. But if you plug them into the machine of string theory, the physical theories you will get in the end are equivalent. So the slogan which is attached to this principle, so the reason why in the end you get equivalent physical theories is that mirror symmetry swaps symplectic geometry and complex geometry. Which is supposed to mean that the symplectic geometry of X is in some mysterious sense equivalent to the complex geometry of X check and vice versa. And so these are some concrete implications for the topological invariance of X. So the most famous one is this exchange of Hodge numbers. The Hodge numbers of X and X check also should establish some form of mirror symmetry of the Hodge diamond, which is where the name mirror symmetry comes from in the first place. And so based on these observations, physicists started to build databases of mirror pairs of Calabi-Yau threefolds, just based on computer searches, essentially. And from some, founded or motivated guesswork, they were able to come up with examples of mirror pairs, even at a time where the precise definition of a mirror pair was still lacking. And so usually this is the point where mathematicians just shake their heads and say, these crazy physicists, what are they doing now? But then attention of algebraic geometers was drawn by a spectacular breakthrough when it turned out that this stuff had some serious implications for enumerative geometry, for instance. Yeah, so this is one of the most famous episodes in the history of mirror symmetry, at least from the point of view of algebraic geometers. So in a very famous paper, Candelas de la Osa, Green and Parks, so they managed to compute so-called Gromov-Witten invariance of the quintic threefold, which is a particular example of a Calabi-Yau threefold, by observing that under this mirror symmetry, these Gromov-Witten invariants, which are hard to compute, are transformed into certain complex period integrals, which are easier to compute. And their predictions turned out to match with everything that algebraic geometers knew at the time, and they went even further than the knowledge of algebraic geometers at the time. So this was a big challenge for algebraic geometry and mathematics as a whole. So we had to explain why such predictions turned out to be correct. And so this was mathematically proven around 95. But even then, I mean, these calculations only concerned one particular pair of mirror Calabi-Yau threefolds. And what was lacking, and which to a certain extent is still lacking today, is a precise mathematical definition of mirror pair plus, well, a more or less effective method to construct such pairs. Yeah, so there was some pioneering work in the 90s by Batirev and Borisov, who considered complete intersections inside toric varieties. But we still need a more general machine in order to systematically produce pairs of this type. And somehow, one of the most interesting attempts to give a geometric explanation for the phenomenon of mirror symmetry is the following conjecture, which was proposed by Strominger, Yau, and Zaslov in '96. And which is called the SYZ conjecture, for the obvious reason. So the statement that I'm going to write down is not exactly the original form of the conjecture. So after the paper was published, people realized that the conditions had to be amended a little bit. So I will present some update of the original formulation, which says the following thing. So suppose that we have a maximally degenerate family, x star over delta star, of complex Calabi-Yau manifolds of dimension n over the punctured disk. Delta star. So what is meant by maximally degenerate? Again, there are different notions that appear in the literature, but the working definition that I will use is that we have semi-stable reduction over the disk. And so this means that we can extend our family over the whole complex disk delta in such a way that the total space is smooth and the central fiber is a reduced strict normal crossings divisor. Plus the monodromy on the middle degree cohomology of general fiber of our degeneration has a Jordan block of maximal rank. which by the monodromy theorem is rank n plus 1. That's right, but I'll come back to this a bit later. But somehow this is a way of formalizing that we want our family to be as degenerate as possible. Yeah. Well, you have to take that up with Adrian. I don't feel responsible for that part of that.
Okay, let's. Sorry. No, but this is not wrong. I guess that we should have, if we have questions at the end of the talk, they have to be by microphone. Because during, when it's better if Johannes repeats the question.
Okay. So the question was, what can we say about the shape of the special fiber for such a semi-stable extension of our family? The answer was, I'll come back to this in one of the following lectures. So for now, let me just say that this is a way to formalize that our family is as degenerate as possible in a certain sense. So then, the expectation is that we have a very particular structure on the general fiber xt. So it should admit fibration, say rho, from xt to the n-dimensional sphere, whose smooth fibers are so-called Lagrangian tori. So Lagrangian tori, this is a notion that comes from symplectic geometry, which I'm not going to explain because somehow it doesn't have any importance for the remainder of the lectures. But you just have to think of this as a statement about the global geometry of a general fiber xt. So we should be able to find this particular type of fibration parametrized by a n-dimensional sphere as n, and whose general fiber has a very nice structure, is a Lagrangian tori. And then as t tends to 0, the fibers of rho are collapsed. Yeah, so you can make sense of this by using a notion of convergence for metric spaces, which is called Gromov-Hausdorff collapse. So again, the definitions for us are not so important. So we just think of the fibers as shrinking as t moves to 0, and in the limit, we're only left with the base of the fibration. So how does this help to explain mirror symmetry? Well, here's a recipe to construct the mirror dual. Xt check is constructed by dualizing the torus fibration over the smooth locus of rho, and compactifying the results. Yeah, so we know that we have a duality theory for tori, which switches character and co-character lattices. So the idea is to apply this duality operation to the fibers of our fibration. We get a dual fibration, at least over the locus where rho is smooth, and then we compactify the result back to a Calabi-Yau manifold. Only life is never that simple. So the most annoying part of the theory, which in any case is conjectural at this point, are so-called quantum corrections. Yeah, so it turns out that in general, this dual torus fibration cannot be compactified to a Calabi-Yau, and you have to deform somehow the complex structure on the dual fibration in order to get a nice compactification. So this is what makes the whole theory extremely complicated, but the good news is that we don't really care for these lectures, because I will focus entirely on the construction of the fibration rho, and I won't say anything else about the problem of reconstructing the dual or the mirror dual Calabi-Yau manifold. So I think it's fair to say that at this point we don't have a whole lot of evidence for the conjecture in this form. But it has generated some very interesting developments in, whoops, I'm very bad at this stuff. It has generated some very interesting developments in algebraic geometry. So this idea of an SYZ fibration was picked up in 2 different programs whose aim is to carry out this type of strategy within the world of algebraic geometry. So 2 programs in algebraic geometry. The first one is due to Gross and Siebert. And I think it's fair to say that this program is most developed at this point. And they've found some very surprising and quite interesting applications to topics ranging from cluster algebras to singularity theory. So the idea is there to use methods which come from tropical toric and logarithmic geometry. However, there's another competing program in a sense, which is the one I want to discuss here, which is due to Kontsevich and Soibelman, and which was kicked off with a beautiful paper in 2006. And their idea is that the correct place to look for the SYZ fibration is, well, not in the world of symplectic geometry, but in non-archimedean geometry. More precisely, in the theory of Berkovich spaces. Over the field of complex Lorentz series, endowed with a p-adic absolute value. And so the aim of these lectures is to explain this construction. And, well, the explanation will include a very brief crash course on Berkovich spaces, or at least a tiny bit of the theory that you need to know in order to understand the construction. And then I mostly want to discuss the relations with MMP and the theory of Igusa zeta functions. Yeah, and so for the second part, so this is all contained in joint work with Mircea and with Chenyang. Okay, so all of this was just motivation. Even if you didn't understand a word of what I said, we'll take a few steps back and start from scratch. So let me fix a couple of notations for the rest of the talk. So I'm going to fix a field of characteristic 0, small k. R will be my notation for the ring of formal power series. Capital K will be its fraction field, so the field of Lorentz series over small k. And then, well, we have some interesting structure on this field. So we have the p-adic valuation. Or equivalently, we can consider the p-adic absolute value, which is given by an exponential of minus this valuation. So when we endow our field of Lorentz series with this absolute value, it becomes a complete valued field. But the absolute value is non-archimedean, which means that we have to be a bit more cunning to do analytic geometry over this field. And so the theory that we are going to use is this theory of Berkovich spaces. I want to say that actually a large part of the story that I'm going to tell extends to positive and mixed characteristic. But since all of the main applications, namely relations with MMP and Igusa zeta functions, only use characteristic 0, I'll just make this assumption from the start. So that I don't have to make any assumptions further on existence of resolution of singularities and so on. But for people who are interested, a big chunk can actually be extended to positive residue characteristic as well. So my first main task is to explain what are Berkovich spaces. And in fact, you will see that the account that I'm going to give is extremely restricted. So the theory is 100 times richer than what I'm going to explain. And in fact, we will need very little. We will only discuss analytifications of algebraic varieties. And we will focus on the underlying topological space. So the Berkovich space comes with an analytic structure, with a sheaf of analytic functions, which we're going to ignore almost completely in these talks, because we don't need it for the applications. So don't be fooled. There's much more to Berkovich geometry than what I'm going to explain. But first, let me explain how we can attach a Berkovich space to an algebraic variety. And this is done by means of a process which is somewhat similar to the way you attach a complex analytic variety to a complex algebraic variety. So we start with a scheme of finite type over our non-archimedean field capital K. And then we can consider the set xn. So xn will be our notation for the Berkovich analytification of x. And as a set, it has a very natural description. So it's just a set of couples, x, consisting of a point psi x and an absolute value, which I will always also denote with an index x. So where psi x is a schematic point of capital X, and my absolute value is an absolute value on the residue field at psi x. So this is an absolute value. Extending our given absolute value on the base field capital K. And so somehow this is the most naive thing you can do. We just take our set of schematic points, and then we upgrade the structure by taking into account the absolute value on the base field. For each of our schematic points, we just consider all the possible ways we can extend our absolute value on K to the residue field at our schematic point. So this defines the identification already as a set. And now we need to turn it into a topological space. So the topology will be the weakest topology, satisfying the following two properties. Well, first of all, we have a map iota, which is called the analytification map. Which goes from the analytification of X back to the scheme X itself. And its definition is pretty straightforward. So we just forget the absolute value, and we only keep the schematic point underlying X. So we send X to its schematic support psi X. And so we want that this is a continuous map. Now, in other words, we're saying that the Berkovich topology on the analytification has to be stronger than the Zariski topology on X. And then we also want nice properties for regular functions, which are defined on our scheme X. So more specifically, we want the following thing. So for every u in X open, and for every regular function f which is defined on U, we can consider the following map. So the map is denoted by absolute value of f. So it's defined on the inverse image of U under iota. So these are just all the absolute values that are centered at points of U. It takes values in non-negative reals, and it sends a point x to, well, we take the function f, we evaluate it in psi x, which we can do because psi x lies in U, where f is defined. So this gives us an element of the residue field at psi x. And on this residue field, x also gives us an absolute value, namely the absolute value which we have indexed by x. And so we also want that this map is continuous for all possible choices of U and f. Yeah? So condition 1 says our topology is stronger than the Zariski topology. Condition 2 says absolute values of regular functions are continuous. And that's it. We just take the weakest topology satisfying these requirements, and this defines the Berkovich topology on X-am. And then, of course, at this point, once you come up with such a definition, you do some kind of sanity check. So you want that topological properties of this space nicely reflect the geometric properties of X. And somehow it has everything you can hope for. So you can show that this identification will be locally compact, will be locally arcwise connected. It's going to be Hausdorff even only if X is separated. It's going to be compact even only if X is proper. And it's going to be connected even only if X is connected. Yeah, so somehow this is a very nice topological space with very nice properties, which faithfully reflect the geometry of X. So that's a strong sign that this is a meaningful construction. But in fact, we will, in practice, need even less than the whole Berkovich space because of the following observation. So I start losing my mic. I don't know if there's something I should do about it, but we'll see. So when psi is a closed point, then the absolute value on k has a unique extension to the residue field at psi, simply because the residue field at psi is a finite extension of k. And so this means that iota minus 1 of psi consists of a unique point, is a singleton. And namely the point given by the schematic point psi together with this unique extension of our absolute value. And somehow these are the boring points because you will see once I start making pictures of Berkovich spaces, these closed points are the points that lie at the boundary of the Berkovich space and which are to a certain extent irrelevant for its topological structure. So the more interesting things happen if we look at non-closed points. So this is far from true if psi is not closed. So in particular, if x is integral and psi is its generic point, well then, what is the inverse image of psi under the identification map? Just by definition, it's a set of all the absolute values on the function field of x. This is just the residue field at the point psi. Extending the absolute value on k. Or to reformulate it in a way which is more familiar to people in birational geometry. So by taking minus natural logarithm, we can also view this as a set of real valuations on the function field of X extending the given discrete valuation on K. And this set is going to be huge.
May I remind you to use button?
Sorry?
Could you use button?
Oh, okay, sure. This set is huge. In a certain sense, it's even a bit too large, because as soon as the dimension of X is at least 2, we don't really have any effective way of classifying all these valuations that live on the function field of X. Yeah. So if dimension of X is at least 2, it's very difficult to visualize. Simply because we don't really understand all the valuations that live on this function field. But we will see that there are some very interesting and important classes of points in this set that we can produce using birational geometry and which are sufficient to control the entire structure of the Berkovich analytification. So we will produce interesting subsets from birational geometry. And show that in a certain sense they control the topology of the whole Berkovich space. At least if X is smooth. Which is the most important case for the applications that I want to present later on. So notation. So this set, the set of real valuations on the function field extending the discrete valuation on K, will be denoted by Xbir. So this is the space of birational points. On X. Birational points because, well, by their very definition, this is a birational invariant of X. And so as a set, this is a set that birational geometers have studied ever since Zariski. But Berkovich geometry gives us more. On this set, we also have a natural induced topology and even an analytic structure which comes from the sheaf of analytic functions on Xn, which we haven't discussed in these lectures. Everything clear so far? Yeah. So then let's try to see how we can use birational geometry of X to produce such birational points. And so the most general class of points that we are going to consider are the so-called monomial points. But, we will get there in 2 steps. So first I'm going to introduce a smaller set, a set of divisorial points, and all the constructions will be based on the geometry of models of X. So let me start with a couple of definitions. So from now on, I'm going to impose some geometric restrictions on X. So X will be connected, smooth, proper case scheme. All right, so a model of X is a proper flat R scheme, curly X, endowed with an isomorphism from the generic fiber of curly X, so the base change to capital K, to the initial variety X. Yeah? So geometrically, we think of X as families of varieties over a punctured, small punctured disk, and a model is just a way to extend this to a family over the whole disk, just like in the setup of the SYZ fibration. And then we will be interested in models with particularly nice properties. So we say that a model is SNC if the total space is regular and the special fiber has strict normal crossings. And so by resolution of singularities, we know that there are lots of SNC models. In fact, they form a cofinal family inside the family of all models of X. However, we will see that, well, a bit later, that it's important to generalize the notion of SNC model. So, no. So the special fiber is not assumed to be reduced. For me, a strict normal crossings divisor is not necessarily a reduced divisor. So it will be important later on to work with a more general class of models for reasons that are related to the minimal model program. So we say that the model is DLT, which stands for divisorially log terminal. Divisorially. If curly X is Q factorial, the pair consisting of curly X and a reduced special fiber is log canonical. And every log canonical center meets the locus where curly X is in fact SNC. So where curly X is regular and where the special fiber has strict normal crossings. So unfortunately, if you haven't seen this definition before, there's very little I can do in this limited time frame to explain what this definition really says. For our purposes, it's important to realize that this is somehow a mild generalization of the class of SNC models. So we allow certain mild singularities on the total space curly X, which somehow don't interfere with the applications to Berkovich geometry. And throughout the results that I'm going to prove in the next lectures, you will actually get a feeling for what these properties really mean. So it turns out that these are designed almost perfectly for the applications to Berkovich geometry and the construction of skeleton.
When you first stated the SYZ conjecture and you said maximally degenerate, were you assuming that the central fiber was reduced there too? Or
That's right. So that was this first condition of semi-stable reduction over the whole disk. Yeah.
here we're not.
No. That's right. So the setup is much more general than the setup for the SYZ conjecture. That's right. So when curly X is a DLT model, then stratum of the special fiber is, by definition, a connected component of an intersection of irreducible components. Of the special fiber. Yeah, so we produce a standard stratification of the special fiber according to which components pass through your points. And so from the definition of the DLT model, one deduces the following fact. So the strata are precisely the log canonical centers in this case. And in particular, each of them meets the locus where our model is SNC. And so this is the first crucial observation. Some of the constructions that I'm going to make in order to produce these monomial points on Berkovich spaces, they are local at the generic points of the strata. And since these generic points automatically lie in the SNC locus, for these constructions it doesn't matter at all whether you work with DLT models or with SNC models. So that's the first important feature of the definition of a DLT model. Okay, so now let's try to produce some Berkovich points from the geometry of these models. And the simplest construction you can come up with is construction of divisorial points. So let curly x be any normal model of x over R. And let E be an irreducible component of the special fiber of multiplicity n. And so we all know that once we've chosen such a component, we can write down valuation on the function field of x, namely the associated divisorial valuation, which just computes the order of a rational function along the component E. And so such a divisorial valuation almost defines a Berkovich point, except that in the definition of Berkovich point, I also require that the valuation extends the given valuation on the base field K, which means that the parameter T should go to 1. In this case, the parameter T will go to n. That's basically the definition of the multiplicity of my component. So in order to get a Berkovich point, I rescale by dividing by n. So then this becomes a divisorial valuation, extending the discrete valuation on K. And so to such a valuation corresponds a point x in the space of birational points of x, which is called the divisorial point associated with the model curly x and with the choice of irreducible component E in the special fiber. So there's good news and bad news about these points. The good news is that there are plenty of divisorial points. So the good news is that the divisorial points are actually dense in the whole Berkovich space. Yeah, so every Berkovich point can be approximated by divisorial points, which gives us some geometric control over all the points that live in our Berkovich space. But the bad news is that the induced topology on this set is very ugly. So the topology is totally disconnected. Meaning that it tells us essentially nothing about the topology on the Berkovich identification Xn, which will be a nice connected topological space. So we have to work a little harder. And so the next step in the construction is to glue the divisorial points together. Using monomial points.
Don't we need R multiples to the divisorial?
I'm sorry?
Don't we need like real multiples of the divisorial one?
These won't live in my Berkovich space because they will no longer extend the given valuation on K. So the condition that the valuation of T needs to be 1 gives me a slice in the valuation space. That's right. So monomial points are given by so-called monomial valuations. So this is a very classical object in the theory of valuations in birational geometry. And somehow they can be viewed as interpolations between divisorial points. So I will not give you the precise construction. I mean, it's pretty elementary, but I have to make some sacrifices for reason of time. I just want to explain to which data we can associate such monomial points. So data are the following. So now it becomes important that we take for curly X the DLT model of X. And we choose a stratum, C, of the special fiber. We denote by E1 to ER the irreducible components of the special fiber passing through C. And then so what makes this construction interesting is that we also have a continuous set of parameters that we can use to build our interpolations. Alpha 1 to alpha r. So these are non-negative real numbers. Such that. So this satisfies a normalization condition, which says that if we multiply, I forgot to introduce one piece of notation. So this satisfies the rule that the sum of the alpha I times the ni is equal to 1, where ni is the multiplicity of ei in the special fiber. Yeah, but so these parameters can vary continuously inside the simplex, which is defined by these conditions. And so to this data, we can attach a point in Xn or even in Xb, so a real valuation on the function field called the monomial valuation or the monomial point associated with, well, all the data that I've chosen. So curly x, C. Then I have my components E1 to ER, which are determined by C. And I have my tuple of parameters alpha. And so what we're going to see next is that these monomial points, well, on the one hand, they're sufficiently geometric to understand them in more or less explicit terms. And on the...
Are the EIs chosen, or do you take all irreducible components?
I take all of them. So the only reason to include them in the notation is because the order is important, since each alpha I is attached to an EI. That's right. So I could have reversed the order. I could first have chosen the components and then chosen one connected component of their intersection, which probably would have made more sense. So we'll see next time that these monomial points, they form a very nice subspace of the Berkovich space, whose topology we can describe completely explicitly. And this subspace is big enough to determine the homotopy type of X. And even the whole topological space X on. But yeah, let me stop here for today. Thanks for your attention.